Hi, I'm Jim. Welcome back to my YouTube channel. Today we're going to talk about how to demonstrate Bernoulli's principle in a legitimate way. Most of the demonstrations that you see out there, people blowing between balloons or blowing over a piece of paper and the paper rises up, purport to be demonstrations of Bernoulli's principle, but in fact have little to nothing to do with Bernoulli's principle. And in a previous video I went into that in great length, explaining why blowing over a piece of paper has nothing to do with Bernoulli. The fact that the paper comes up is more related to the Quanda effect, and if you go to Wikipedia, they've got some nice illustrations of the Quanda effect that are actually better than the illustrations in my video, but that's life. Okay, so how do we do it legitimately? The really only good way that I come up with is a Venturi. A Venturi does a nice job. So I have created a Venturi in FreeCAD and drawn it up, and I've sent the files over to Thingverse, and there'll be a link in the description where you can download the 3D printing files. There'll be this nifty drawing that you can use with the dimensions, because it's hard to see what's inside there, and also a cutaway like this that you can print. And these print nicely just standing up on your 3D printer. And these hook up to your standard utility vacuum, okay? I know it says 4 horsepower on that one. That's not real. You can't get 4 horsepower out of a standard US 120 volt 15 amp socket. That just isn't there, okay? Okay, to use this thing, there's a couple ways we can do it. One would be to take the static pressure and dynamic pressure from the ports that are attached here and here. I haven't put it in the cutaway, but there they are. And again, this port here has just got that small hole drilled up at the top. I have no idea if it's focused. And then this is just stuck in, so it measures the pressure on the side. And that gets you pressures, the dynamic pressure from that little hole, the static pressure here, and then you get the same measurements there, and you know the cross section here, you know the cross section there, you can do all the math. The other option would be to make some static and dynamic probes. The total pressure or Pitot tube is just open on the end, and then this one is got a little dab of epoxy in the end and some holes drilled in it to measure the static pressure, just the ambient pressure. And I have these marked when I slide them in. So that mark is the beginning of the Venturi. That mark is where the holes are about lined up right here. I got another mark there. And you could get the same measurements lining those marks up that you get with these probes. Or you could mark this, say, in centimeters or inches from the tip, and then as you go down you can collect the data, and you'd have the measurements here from the drawings, and you could even measure it directly on this cutaway. And you could plot things like pressure versus position as you go down, okay? One problem here is in this Venturi, to make it easy to 3D print on normal typical size printers, standing up, I had to limit the height. So this diverging area here behind the Venturi is way too steep, way too angled, okay? So once you get past here, the pressure, its term is pressure recovery, how much of the original pressure you get back is really bad, and your measurements fall apart, and forget about Bernoulli from there down, okay? Of course, that would be another thing you could do, is maybe make a 2-piece Venturi, so you can make it taller and make this more of a gradual thing, and you could measure pressures on the way in and the way out, okay? Now, what we expect is we have ambient pressure out here, right? It has a total pressure. The air's not moving, okay? We have a total pressure equal to atmospheric pressure, okay? And as it comes in, the streamline coming in, this streamline should maintain the same total pressure as the atmosphere. So our pitot tube here should measure the same pressure and the same pressure here in the pitot tube, or if we're using the pitot probe, you know, there shouldn't be much change in the total pressure or pitot pressure as we come back, okay? Because according to Bernoulli's principle, the total pressure remains the same. The things that change are the static pressure and the velocity. So, you know, given the same mass flow here as here, the velocity has to go up to get the mass through, right? That's just conservation of mass. And as that velocity goes up, the static pressure goes down, okay? The pressure you'd measure at the walls or with the static probe with the holes. But the dynamic pressure, the total pressure, measured by the pitot tube, should remain the same. And any loss in pressure is just due to friction and turbulence. And if you were to, when we go back, measure the total pressure in here, you see we get a lot of losses, okay? So that's how you could use it. You can use it just the 2 points, do the math, you can do graphs. It's up to you. And, you know, another science project, if you want, would be to explore changing this portion of it to see if you could get better pressure recovery and maintain that same total pressure or close to it further down, okay? So with that, let's fire up our vacuum cleaner and we'll take some measurements on this Venturi right here. So first we're going to look at the pitot pressure, which according to Bernoulli should be constant because that's the total pressure. We'll start by using the probes that are built into the Venturi, and as you can see here, just connect to atmosphere, the total pressure is 0 on our manometer. Plugging into the upstream or first pitot tube, we get, again, almost the same reading from our U-tube manometer as you'd expect from Bernoulli's theorem. And then we can move back to the probe right in the throat. You can see a little bit of vacuum, but I think that's more due to my hole not being perfectly aligned than it is due to the losses in the Venturi based on the results we're going to see in just a moment. So there's our pitot probe, which is just a tube open on the front, and we'll start out by pushing it all the way forward so it's sticking out the front of the Venturi, and we can see that the pressure is 0. And when I pull it back into that curve area right there, still no change in the total pressure or pitot pressure. Pull it back to the first probe right about there where my finger is, still 0. Just checking it. We can pull it back a little bit further to the throat of the Venturi, and again our pitot pressure or total pressure stays 0. Little wobble there where the problem is when we go further back, because that Venturi diverges too rapidly, we get a lot of losses, and then the total pressure goes way down, and at that point basically Bernoulli has left the room because we no longer have our conservation of energy along that streamline. It's just too much turbulence and loss. Looking at the static pressure, or the pressure on the walls of the Venturi, we'll start by looking at the upstream port, and that is going to show a little bit of suction because we've accelerated the air into the Venturi from our surrounding atmosphere. And we go down to the narrow part or throat of the Venturi, and you'll see a little over 4 kilopascals of suction there, or low pressure. Again, in accordance with Bernoulli, right? This is what Bernoulli predicts, along with conservation of mass. Now we can take our static probe, the continuous probe, in spite of the fact I put the holes in the wrong spot, it still gives us pretty good results. So I can slide it in to my adapter, slide it all the way forward, almost to the entrance of the Venturi. I'll point where it is right there on that cutaway. And we're seeing a little bit of suction as you start coming in the Venturi. Pull it back to the mark that lines it up with that first port, and you can see about the same suction we saw at that port. And we'll pull it back to the second port in the throat of the Venturi, and again we'll get just over 4 kilopascals like we got before, as we expect. All very nice and Bernoulli. And I'm going to slide it about halfway in between at a medium diameter, just to show you how you can pick up pressures at different points in the Venturi if you wanted to. Okay, I believe I mentioned that the U-tube manometer is just a U, water and food coloring, and then this is open at the top, and then this one just goes to the hose that I connected everything else to. Okay, and you want it more level than it is right now. Things got knocked down. So for the probes, this is 1/16 brass tubing from the hobby shop. I don't know what metrics equivalents are available, but in any case, when you're putting it in, if it's a little too tight, you can just run a drill through the hole, and I would check the fit of the fatter tube as well before committing to sticking the skinny tube in. You know, that fits kind of tight, but you could drill it out ahead of time. This one is under the surface, but there's no reason you can't have it stick out like that far to make it easy to twist and align, because you want this 1/16 inch hole. Oh, there we go. Yeah, there's no reason it can't stick out like that. This particular, did I say that was 1/16 inch tube? That's 1/8 inch tubing. 1/8 being, you know, about 2.5 millimeters in diameter, and that hole is a 1/16 of an inch in diameter, which is about a millimeter and some odd. I don't know. I'll let you do the math. And then the end of this tube is just plugged with a little dollop of 5-minute epoxy, and you can stick this in. So even if it's sticking out like that, when you put this on over it, who cares, right? But in order to drill that hole, it's really hard to get a hole right, you know, on top of. I can pull it out completely. There. It's really hard to get a drill started on the top of this rounded surface, and if you try to center punch, this stuff is so thin and soft, that's a problem. So what I did is I have this chunk of maple. I drilled the 1/8 inch hole through this way for, well, let me grab. So the 1/8 inch hole goes through like that, and then as close and square as I could, I drilled a 1/16 inch hole through there, and then that's kind of my drill guide, so that when I can drill the hole in the tube without it wandering quite so much. It's not perfectly square. Okay, this is the static probe here. Again, the 1/8 inch tubing. I've got marks on it here and here that indicate when it's lined up about with this position or that position. But again, you can mark it in millimeters and get a continuous data collection, of course, and graph that if you prefer. so you can calculate velocities or mass flows and see how they all compare at different points along that Venturi. To adapt it to my vinyl hose, I just literally wrapped it up with some tape until it was a tight fit. Nothing very sophisticated. Again, the end is plugged with a little bit of epoxy, and you want about 8 tubing diameters. So if this is a 1/16, that would be 8/16, half an inch, or 12.5 millimeters, 12.25 millimeters from the end to where these holes are drilled. Okay. These, set them on the print sitting on the bed like this without supports, the cutaway and the Venturi. There's no problem. The overall height is short enough, it'll fit most printers. This one I printed this way, but I did turn on the supports using Kira slicer with the tree supports. They pop out pretty quick and clean and easy, both inside and out where it needs support. So that worked out easy to print. Pitot tube is just the tubing open on the end, and again my marks for the various positions. That's held on with blue tape. These are just pressed in, and you can see hopefully the holes are lined up pointing directly at the inlet. They're just pressed in. If they're too loose, you can use a drop of 5-minute epoxy to hold them in place. If they're too tight, just run a drill bit through there so that they go in. It's really not hard to assemble. It's got feet so you can set it down when you're doing your experiment or displaying it, or you can stand it on end, it doesn't matter. I may have mentioned that 1 kilopascal is almost exactly 4 inches of water, so since they go one up, one down, putting these graduations 2 inches apart works out as close to being exact as you're going to do with Sharpies and drawing things by hand. And I think that's all of the parts, the bits and pieces involved in making this work. If you choose to not use these, it'd probably be a good idea to put a little something, a little epoxy or something in the holes so that they're plugged. Give you more consistent readings, or you can modify the STL files, or I put them up on Thingverse in several formats. STL files, or no, I did 3MF files, SCAD files, step files, and if you want the native FreeCAD files, just drop me a note and in the comments, and I'll upload them. Okay, well with that I'll say thank you for watching this. I hope you found it at least entertaining and perhaps gave you some ideas for your science fair project. I would encourage you to watch the previous video, which is linked down in the comments, because that one actually gets into all the math behind Bernoulli's principle and that sort of thing, and explains, again, why blowing over a sheet of paper has nothing to do with Bernoulli. And I think that's it, so I'll catch you on the flip side.